Tonight, we're going to confront a possibility that most people have never considered. What if everything we think we know about the forces governing the universe is incomplete? Right now, physics recognizes four fundamental forces: gravity, electromagnetism, the strong force, and the weak force. Together, they explain virtually everything, from why apples fall, to why stars shine, to why atoms hold together. Four forces, that's it. But here's what keeps certain physicists awake at night. There are cracks. Tiny, persistent, unexplained cracks in our measurements. Particles behaving in ways they shouldn't. Galaxies moving in ways nothing can account for. Experiments producing results that none of the four known forces can explain. What if the universe has been hiding a fifth fundamental interaction this entire time? One we haven't been able to isolate. One operating just beyond the edge of what our instruments can confirm. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe genuinely helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with a deceptively simple question. What holds the universe together? Not poetically, not philosophically, physically. What are the actual interactions responsible for everything that happens in this universe, from the way a planet orbits a star, to the way a nucleus holds itself together, to the way light travels across billions of light years of empty space to land on your eye? Physics has an answer, and for the last several decades, that answer has been remarkably clean. There are four fundamental forces of nature. Just four interactions that account for every physical event ever observed, every chemical reaction, every beam of light, every nuclear explosion, every heartbeat, every supernova. Four forces, that's the whole list. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These four interactions form the foundation of modern physics. They are what every equation ultimately points back to. Every time something pushes, pulls, attracts, repels, binds, decays, radiates, or transforms in this universe, one or more of these four forces is responsible. Remove any single one, and the universe as we know it ceases to exist. Not figuratively, literally. If you removed gravity, there would be no stars, no planets, no galaxies. Matter would drift without structure. If you removed electromagnetism, atoms couldn't form, chemistry wouldn't exist, light wouldn't exist, you wouldn't exist. If you removed the strong force, atomic nuclei would fly apart instantly. Every atom heavier than hydrogen would disintegrate. If you removed the weak force, the sun wouldn't shine, because the specific nuclear reactions that power stars depend on the weak force to convert protons into neutrons. These are not minor details. These four forces are the architecture of reality. They determine what exists, what can exist, and how everything interacts. And yet, there are things they can't explain. Measurements that don't add up. Observations that sit outside the predictions. Phenomena that none of these four forces can fully account for. And this is what keeps a certain kind of physicist up at night. Not the successes, the gaps, the lingering, stubborn, unexplained cracks. But before we can understand what a fifth force might be, we need to understand what a force actually is in physics. Because the word force gets thrown around loosely. You hear it in everyday language all the time. Willpower, political force, force of habit. But in physics, force has a very specific meaning, and that meaning has changed over the centuries as our understanding has deepened. In the simplest terms, a force is an interaction between objects or particles that causes a change. It can push, pull, attract, repel, bind things together, or cause them to decay. Isaac Newton gave us the first great mathematical framework for understanding forces. His law of universal gravitation described how every object with mass attracts every other object with mass. His three laws of motion described how forces change the motion of objects. For over 2 centuries, this framework worked beautifully. It predicted planetary orbits, it explained tides, it let engineers build bridges and machines. But Newton's picture was incomplete. He described what forces do, but not what they are at a fundamental level. He couldn't explain how gravity actually worked across empty space. How does the Sun reach out across 93 million miles and pull on the Earth? Newton himself admitted this was a problem. He famously wrote that the idea of one body acting on another through a vacuum without anything mediating the interaction was an absurdity. He had no mechanism, he just had the math. Modern physics has a much deeper picture. Today, we understand fundamental forces through the framework of quantum field theory. And here's the key idea. Every fundamental force is carried by a field that permeates all of space, and the interaction itself is mediated by particles. These mediator particles are called bosons. When two particles interact through a fundamental force, what's really happening is that they're exchanging bosons. The bosons carry energy and momentum between the interacting particles, and that exchange is what we experience as a force. Think of it this way. Imagine 2 people standing on ice, and one throws a heavy ball to the other. The thrower recoils backward, the catcher gets pushed backward when they catch it. By exchanging the ball, both people have changed their motion. They've exerted a force on each other through the exchange of an object. This is a crude analogy, but it captures the essential idea. Forces arise from the exchange of mediator particles. This framework is called the Standard Model of Particle Physics. It's one of the most successful scientific theories ever constructed. It describes 3 of the 4 fundamental forces and catalogues all known elementary particles. The Standard Model has been tested to extraordinary precision over decades and has passed every test. Its predictions match experimental results to many decimal places. It is, by almost any measure, a triumph of human understanding. Let's walk through the 4 forces, not as a history lesson, but to understand what each one does, what carries it, and where it operates. Gravity is the most familiar force. It's the one you feel every moment of your life. It's why you stay on the ground. It's why things fall. It's why planets orbit stars, why stars orbit the centers of galaxies, why galaxies cluster together across hundreds of millions of light years. Gravity acts on anything that has mass or energy, and it has infinite range. It gets weaker with distance, but it never disappears entirely. The gravitational pull between you and a star on the other side of the galaxy is not zero. It's unimaginably small, but it's not zero. Albert Einstein fundamentally reshaped our understanding of gravity in 1915 with his general theory of relativity. Einstein showed that gravity isn't a force pulling objects toward each other through empty space. It's a consequence of the curvature of space-time itself. Mass and energy warp the fabric of space-time, and objects move along curved paths through that warped geometry. The Earth doesn't orbit the Sun because an invisible rope is pulling it. It orbits because the Sun's mass curves space-time, and the Earth follows the straightest possible path through that curved geometry. General relativity has been confirmed by countless experiments. It predicts gravitational lensing, where light bends around massive objects. It predicts gravitational time dilation, where clocks run slower in stronger gravitational fields. It predicts gravitational waves, ripples in space-time that were directly detected for the first time in 2015 by the LIGO observatory. But here's the thing about gravity that matters for our story. Despite being the most familiar force, gravity is the odd one out. It is by far the weakest of the 4 fundamental forces, enormously, absurdly weaker. The electromagnetic force between two protons is roughly 10 to the 36 times stronger than the gravitational force between those same two protons. That's a 1 followed by 36 zeros. Gravity is so weak at the particle level that it's essentially invisible to particle physicists. You can ignore it completely in particle physics experiments and lose nothing in your calculations. The standard model doesn't even include gravity. It describes 3 forces, not 4. Gravity sits outside the framework, described by general relativity, which is a completely separate theory using different mathematics, different assumptions, and different rules. Nobody has successfully unified gravity with quantum mechanics into a single consistent theory. This is one of the biggest unsolved problems in all of physics. And it's worth remembering as we talk about the possibility of a 5th force, because if we can't even fully reconcile the 4 forces we know about, how confident can we be that there isn't another one hiding in the gaps? Electromagnetism is the second fundamental force. It's responsible for almost everything you experience in daily life beyond gravity. When you touch a table and your hand doesn't pass through it, that's electromagnetism. The chemical bonds holding molecules together are electromagnetic. Light is electromagnetic radiation. Radio waves, microwaves, X-rays, gamma rays, all electromagnetic. The entire field of electronics, every circuit, every computer, every phone, runs on electromagnetism. Electromagnetism acts on particles that have electric charge. It can attract opposite charges and repel like charges. Like gravity, it has infinite range. But unlike gravity, it can be both attractive and repulsive, which means it can cancel out. A neutral atom has equal positive and negative charges, so its electromagnetic force at a distance is effectively 0. This cancellation is why gravity dominates at cosmic scales, even though it's vastly weaker. Gravity only attracts, it never cancels. The mediator particle of electromagnetism is the photon. When 2 charged particles interact, they exchange photons. Every electromagnetic interaction, every flash of light, every chemical bond, every radio signal involves photons being exchanged between charged particles. The photon has no mass, which is why electromagnetism has infinite range and why light travels at the speed of light. In the 1860s, James Clerk Maxwell unified electricity and magnetism into a single framework, showing they were 2 aspects of the same force. This was one of the great unifications in physics history. What seemed like 2 separate forces turned out to be one force viewed from different angles. Maxwell's equations remain one of the most beautiful and powerful sets of equations in all of science. The strong nuclear force is the most powerful of the 4 forces, but it operates at the tiniest scales. Its range is roughly the size of an atomic nucleus, about 10 to the minus 15 meters. Beyond that distance, it essentially vanishes. The strong force does 2 things. At the most fundamental level, it binds quarks together to form protons and neutrons. Quarks never exist alone. They are always confined inside composite particles called hadrons. The strong force is so powerful that if you try to pull 2 quarks apart, the energy you put in creates new quarks rather than freeing the originals. This is called confinement, and it's one of the most remarkable properties of any force in nature. You literally cannot isolate a quark. At a slightly larger scale, the strong force also binds protons and neutrons together inside atomic nuclei. This is sometimes called the residual strong force, or the nuclear force. It overcomes the electromagnetic repulsion between positively charged protons, which would otherwise blow every nucleus apart. Without the strong force, only hydrogen could exist. No carbon, no oxygen, no iron, no heavy elements at all. The periodic table would have 1 entry. The mediator particles of the strong force are called gluons. There are 8 types of gluons, and they carry a property called color charge, which is the strong force equivalent of electric charge. The theory describing the strong force is called quantum chromodynamics. Gluons are massless like photons, but they interact with each other, which is very different from photons. Photons don't carry electric charge, so they don't interact with each other directly. But gluons carry color charge, so they do interact with each other. This self-interaction is what makes the strong force so complicated and so difficult to calculate. It's also what gives rise to confinement. The weak nuclear force is the most subtle and, in some ways, the strangest of the four. It's responsible for certain types of radioactive decay, where one type of particle transforms into another. The most common example is beta decay, where a neutron inside an atomic nucleus transforms into a proton, emitting an electron and an antineutrino in the process. The weak force is the only force that can change the flavor of a quark, meaning it can turn one type of quark into a different type. An up quark can become a down quark or vice versa, but only through the weak interaction. This is crucial for the nuclear reactions that power stars. Inside the Sun, hydrogen nuclei fuse together to eventually form helium. But this process requires protons to convert into neutrons at certain steps. Only the weak force can do this. Without the weak force, the specific fusion chain that powers the Sun wouldn't work. Stars would need a completely different energy source, and it's not clear one would exist. The weak force has an extremely short range, even shorter than the strong force. It operates at distances less than about 1% of the diameter of a proton. The mediator particles of the weak force are the W and Z bosons. Unlike photons and gluons, these bosons are massive. The W boson has a mass of about 86 times the proton's mass. The Z boson is even heavier at about 97 times the proton's mass. Their enormous mass is why the weak force has such a short range. Heavy mediator particles can only travel short distances before they decay, which limits how far the force can reach. In the 1960s and 70s, physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that electromagnetism and the weak force are actually two aspects of a single, unified force called the electroweak force. At very high energies, the kind that existed in the first moments after the Big Bang, these two forces behave as one. But at the lower energies we experience in everyday life, the symmetry between them is broken and they appear as separate forces with very different properties. This unification was confirmed experimentally when the W and Z bosons were discovered at CERN in 1983. It was another great triumph, showing that forces that seem separate might share a deeper identity. So that's the picture: 4 fundamental forces, 3 described by the Standard Model, 1 described by general relativity. Together, they account for virtually every physical phenomenon ever observed. The Standard Model has been tested in laboratories around the world for over 50 years. Its predictions for particle masses, interaction strengths, decay rates, and scattering amplitudes have been confirmed to extraordinary precision. Some of its predictions have been verified to better than 1 part in a billion. This is not a rough sketch. This is one of the most precisely tested theories in the history of science. And yet, there are things it cannot explain. Not small, obscure academic things. Fundamental, glaring, enormous things. Start with the most obvious. The Standard Model does not include gravity. It describes 3 forces, not 4. Gravity sits outside the framework entirely. For decades, physicists have tried to bring gravity into the quantum fold, to create a quantum theory of gravity that's consistent with the Standard Model. So far, nobody has succeeded. The mathematics breaks down. The calculations produce infinities that can't be removed. General relativity and quantum mechanics, the 2 most successful theories in physics, are fundamentally incompatible at extreme scales. This isn't a minor inconvenience. It's a sign that something deep is missing from our understanding. Then there's dark matter. Astronomers have known since the 1930s that galaxies don't behave the way they should based on the matter we can see. Stars at the outer edges of galaxies orbit far too fast. They should fly off into space, but they don't. Something invisible is holding them in. Observations of galaxy clusters, gravitational lensing, and the cosmic microwave background all point to the same conclusion. About 27% of the universe's total mass and energy consists of something that interacts gravitationally but doesn't emit, absorb, or reflect light. We call it dark matter, but we don't know what it is. No particle in the Standard Model accounts for it. Despite decades of searching with underground detectors, particle colliders, and space telescopes, dark matter has never been directly detected. It interacts with gravity. It might interact with other forces, but we don't know which ones, or whether it interacts through a force we haven't discovered yet. Then there's dark energy. In 1998, two independent teams of astronomers discovered that the expansion of the universe is accelerating. Distant galaxies are flying apart faster and faster over time. Something is driving this acceleration, pushing the universe apart against the pull of gravity. This something, called dark energy, makes up roughly 68% of the universe's total energy content. We have almost no idea what it is. It could be a property of empty space itself. It could be a new field permeating the cosmos. It could involve an interaction that doesn't fit neatly into any of the four known forces. Dark energy is the dominant component of the universe, and we cannot explain it. And then there are the anomalies. Precision experiments measuring the properties of fundamental particles have revealed small but persistent discrepancies between what the Standard Model predicts and what experiments measure. The muon, a heavier cousin of the electron, has a magnetic property that has been measured to extraordinary precision. The measured value doesn't quite match the Standard Model prediction. The discrepancy is small, but it has persisted across multiple experiments over years. Something might be tugging on the muon that the Standard Model doesn't account for. In nuclear physics, a team in Hungary observed unexpected behavior in the decay of certain atomic nuclei. Behavior that could be explained by a previously unknown particle mediating a previously unknown interaction. The result hasn't been confirmed by independent laboratories, and it remains controversial, but it hasn't gone away either. These are not isolated curiosities. They are symptoms of a deeper issue. The four known forces, spectacular as they are, leave too many questions unanswered. The universe is made mostly of things we can't explain. Particles behave in ways we can't predict. The largest and smallest scales of physics refuse to fit together. This is the context in which physicists ask the fifth force question. Not as science fiction, not as wild speculation, but as a precise, testable scientific hypothesis. What if there is a real, physical interaction beyond the four we know? Not a metaphor, not a vague concept. A genuine force of nature, mediated by a specific particle, generated by a specific field, producing measurable effects on matter. A force that has eluded detection, not because it doesn't exist, but because it's too weak, or too short-ranged, or too cleverly hidden by its own physical properties to have shown up in the experiments we've run so far. This is what we're going to explore. Where the cracks in our understanding appear. What a fifth force would need to look like physically. Why it hasn't been found despite decades of searching. And why, if it ever is confirmed, it wouldn't just add a fifth line to a list. It would restructure the foundation of physics. It would mean there's a field we've never detected, a particle we've never seen, an interaction woven into the fabric of reality that has been operating silently since the beginning of time. It would mean the architecture of the universe is different from what we thought. Not slightly different, fundamentally different. Every force we've discovered has transformed our understanding of reality. When Newton identified gravity, it unified the heavens and the earth under a single law. When Maxwell unified electricity and magnetism, it revealed that light itself was electromagnetic radiation. When the strong force was understood, it explained why matter is stable. When the weak force was characterized, it explained how stars burn and how elements are forged. Each force wasn't just added to a list, each one rewrote the rules. A fifth force would do the same. It would mean the standard model, as successful as it is, captures only part of the story. It would mean there are particles yet to be discovered, fields yet to be measured, interactions yet to be understood. It would open a door to physics beyond anything we currently know. And the most unsettling part? The hints are already there. Faint, ambiguous, unconfirmed, but persistent. Experiments keep finding things that don't fit, results that hover just beyond the edge of what the four known forces can explain. Whether those hints will eventually lead to a confirmed fifth force or evaporate under closer scrutiny is one of the most important open questions in physics today. The universe has surprised us before. Every time we thought we had the complete picture, reality turned out to be deeper, stranger, and more intricate than we imagined. There's no law of nature that says 4 is the final number. There's no principle that guarantees our current list is complete. The only thing that determines how many forces exist is the universe itself. And the universe is under no obligation to make that number convenient or final. So the question isn't whether a fifth force is a nice idea. The question is whether nature actually contains one. And the only way to answer that is to look, to measure, to test, to push our instruments to their limits and see what the data says. That's what physicists have been doing for decades, and what they've found so far is more interesting, more provocative, and more uncertain than most people realize. Science doesn't advance smoothly. It doesn't glide forward in a straight line from one discovery to the next. The real progress, the kind that changes everything, almost always starts with a crack, a measurement that doesn't quite match the prediction, a number that's slightly off, an observation that sits just outside what the theory says should be possible. Most of the time, these cracks turn out to be nothing. A mistake in the calculation, a flaw in the equipment, a statistical fluke that vanishes when you collect more data. But every once in a while, a crack refuses to close. You check the math, you rebuild the instrument, you repeat the experiment, and the crack is still there. Quiet, stubborn, unexplained. Those are the cracks that matter. Those are the cracks that sometimes lead to revolutions. And right now, in physics, there are several cracks that have persisted for years, some for decades, and none of them have gone away. Let's start with the muon. The muon is a subatomic particle, a heavier cousin of the electron. It has the same electric charge as an electron and behaves the same way in most respects, but it's about 207 times more massive. Muons are unstable. They decay in about 2 millionths of a second, transforming into an electron and 2 neutrinos. But in that brief lifetime, muons can be studied with incredible precision, and one particular property of the muon has become the center of one of the most important debates in modern physics. That property is its magnetic moment. Every charged particle that spins, and the muon does spin, acts like a tiny magnet. The strength of that magnetism is characterized by a number called the G factor. For a perfectly simple particle described only by basic quantum mechanics and special relativity, the G factor would be exactly 2. But the real world is not simple. The muon doesn't exist in isolation. It's constantly interacting with the quantum fields surrounding it. Virtual particles flicker in and out of existence around the muon, briefly popping up from the vacuum before disappearing again. Each of these fleeting interactions nudges the muon's magnetic moment slightly away from that clean value of 2. The difference between the predicted G factor and the simple value of 2 is called the anomalous magnetic moment, and physicists refer to this measurement as G-2. Here's why this matters so much. The anomalous magnetic moment can be both measured experimentally and calculated theoretically using the standard model. If the measurement and the calculation agree, it means the standard model accounts for everything that's tugging on the muon. Every virtual particle, every quantum field, every interaction is captured by the theory. But if the measurement and the calculation disagree, it means something is tugging on the muon that the standard model doesn't know about. Something invisible, some interaction that isn't in the equations. And this is exactly what happened. Starting in the late 1990s, a series of experiments at Brookhaven National Laboratory in New York, known as Experiment E821, measured the muon's G-2 with extraordinary precision. The result was slightly but consistently higher than what the standard model predicted. Not by a lot. The difference was tiny in absolute terms, but given the precision of both the measurement and the calculation, the discrepancy was statistically significant. Physicists characterize the reliability of a result using a unit called sigma. A 3 sigma result means there's roughly a 1 in 700 chance the discrepancy is a statistical fluke. A 5 sigma result, the gold standard for a discovery in particle physics, means there's roughly a 1 in 3.5 million chance the result is due to random chance. The Brookhaven result sat at about 3.5 sigma. Interesting. Suggestive. But not conclusive. Not enough to claim a discovery. So physicists did what they always do. They built a better experiment. At Fermilab, outside Chicago, a new experiment was constructed specifically to measure the muon's G-2 with even greater precision. The experiment uses a massive superconducting magnetic ring, 50 feet in diameter, that was originally built at Brookhaven and transported in one piece to Fermilab in a spectacular journey across land and sea. Inside this ring, muons are injected at nearly the speed of light and circle the ring thousands of times while their spins precess, rotating slightly with each orbit. By measuring exactly how that spin precesses as the muons circle the ring, physicists can determine the G-2 value to extraordinary accuracy. The Fermilab experiment released its results in stages. The first results came in 2021, then more data followed in 2023, and the final combined result, incorporating all data collected over years of running, confirmed what Brookhaven had first suggested. The measured value of the muon's anomalous magnetic moment is higher than the traditional standard model prediction. The combined world average, merging the Brookhaven and Fermilab results, shows a discrepancy of roughly 5 sigma from the long-standing theoretical calculation. 5 sigma, that's the discovery threshold. But here's where the story gets complicated. And this is important because it shows how careful real science has to be. The theoretical prediction for G-2 is extraordinarily difficult to calculate. The calculation involves contributions from all 3 forces in the standard model: electromagnetism, the strong force, and the weak force. The electromagnetic contributions are known to stunning precision. The weak force contributions are well understood. But the contributions from the strong force, specifically a component called the hadronic vacuum polarization, are brutally hard to compute. For decades, physicists estimated this contribution using experimental data from electron-positron collisions, plugging measured results into the theoretical framework. This approach gave the prediction that disagrees with the muon measurement. But in recent years, a different method has emerged. Using raw computational power, physicists have begun calculating the hadronic vacuum polarization directly from the fundamental equations of the strong force, using a technique called lattice calculations. And some of these lattice results, particularly from a European collaboration, give a theoretical value that's closer to the experimental measurement. If those lattice calculations are correct, the discrepancy shrinks. The crack might close. This means the Muon G-2 anomaly is currently in a state of genuine scientific tension. The experimental result is clear and precise, but the theoretical prediction depends on which calculation method you trust. Both methods have strengths and weaknesses. Resolving the discrepancy between them is one of the most active areas of research in particle physics right now. If the traditional theoretical prediction holds up, and the lattice results turn out to have an unaccounted error, then G-2 is a genuine signal of new physics, possibly a new particle, possibly a new force. If the lattice calculations are confirmed and the traditional method has a flaw, then the standard model might be fine, and no new physics is needed to explain the muon. We don't know yet. And that uncertainty is itself significant, because the fact that we can't rule out a new interaction, even after decades of effort and billions of dollars in experiments, tells you how close we are to the edge of our knowledge. Now let's turn to a very different kind of experiment. In 2016, a team of physicists at the Atomiki Institute for Nuclear Research in Debrecen, Hungary, led by Attila Krasner-Hawkeye, reported something strange. They were studying the nuclear transitions of beryllium-8, an unstable isotope of beryllium. When a beryllium-8 nucleus in an excited state decays to its ground state, it releases energy. Some of that energy can produce pairs of particles, an electron and its antimatter counterpart, a positron. By measuring the angle at which these electron-positron pairs fly apart, physicists can learn about the decay process. What the Atomiki team found was an unexpected bump in the data. At a specific angle of separation, there were far more electron-positron pairs than the standard model predicted. The excess was consistent with what you'd expect if a previously unknown particle with a mass of about 17 megaelectron volts was being produced during the decay, and then immediately splitting into the electron-positron pair. They called this hypothetical particle the X-17 particle. The result was striking. The team later reported seeing a similar anomaly in the transitions of helium-4 nuclei, which was exactly what you'd predict if the X-17 particle were real. A new particle showing up in two different nuclear systems in the same way is much harder to explain as an experimental artifact. It's the kind of consistency you'd expect from a genuine new particle. If the X-17 exists, it could be the mediator of a fifth force. A boson with a mass of 17 megaelectron volts would mediate an interaction with a very short range, acting only over nuclear distances. It would be too heavy to be a photon, and too light to be a W or Z boson. It wouldn't fit into any known force category. It would be something new. Theoretical physicists quickly proposed models where the X-17 could be a new type of gauge boson, a carrier of a previously unknown interaction that couples to protons and neutrons in specific ways. Some models called it a protophobic boson, meaning it would interact with neutrons but barely interact with protons. This unusual coupling pattern could explain why it hadn't been detected in other experiments, which are typically designed to look for particles that interact with protons or electrons. But here's the critical caveat. The Atomiki result has not been independently confirmed. Other laboratories around the world have attempted to reproduce the observation using different setups and different nuclear targets. So far, no independent group has reported a clear confirmation. Some experiments have seen hints, but nothing definitive. The Atomiki team itself has continued to refine their measurements, and they stand behind their results. But in physics, extraordinary claims require extraordinary evidence, and an independent replication is essential before anyone can claim a new particle has been discovered. The X-17 remains one of the most intriguing anomalies in nuclear physics. It hasn't been confirmed, but it hasn't been ruled out either. It sits in that uncomfortable middle ground where the data refuses to be explained away, but also refuses to be elevated to the status of discovery. The search for a fifth force didn't begin with these modern anomalies. It has a history stretching back decades. One of the most famous episodes occurred in 1986 when an American physicist named Ephraim Fishbach at Purdue University reanalyzed data from a classic experiment performed nearly a century earlier. The original experiment was conducted by the Hungarian physicist Loránd Eötvös in the late 1800s and early 1900s. Eötvös built an extraordinarily sensitive torsion balance, a device that measures tiny differences in gravitational attraction, and used it to test whether all materials fall at the same rate regardless of their composition. This principle, known as the equivalence principle, is one of the foundations of general relativity. Einstein's theory rests on the assumption that gravity treats all matter equally. A kilogram of iron and a kilogram of wood should fall at exactly the same rate, experience exactly the same gravitational acceleration. Eötvös confirmed this to remarkable precision. His experiments found no measurable difference between materials. The equivalence principle held. But when Fishbach reanalyzed the original data using modern statistical techniques, he claimed to find a subtle pattern. He argued that there was a tiny systematic difference in how different materials responded to gravity, and that this difference correlated with a property called baryon number, essentially the total number of protons and neutrons in the material. If true, this would mean gravity wasn't the only long-range force acting on matter. There would have to be a fifth force, one that depended on the composition of an object rather than just its mass. Fishbach proposed that this force had a range of roughly a few hundred meters to a few hundred kilometers, making it far shorter ranged than gravity, but far longer ranged than the nuclear forces. The proposal generated enormous excitement in the physics community. A fifth force would be a monumental discovery. Experimentalists around the world rushed to test the claim using improved torsion balances, pendulum experiments, and measurements in mine shafts, boreholes, and ocean trenches. The results came in quickly, and they were negative. Experiment after experiment found no evidence for a composition-dependent fifth force at the ranges and strengths Fishbach had proposed. His reanalysis of the Eötvös data was scrutinized and found to rest on questionable statistical choices. The anomaly he identified could be attributed to systematic errors in the original century-old measurements rather than new physics. By the early 1990s, the scientific consensus was clear. Fishbach's proposed fifth force did not exist. The equivalence principle held to even greater precision than Eötvös had originally demonstrated. But the episode was not a waste. Far from it. The intense experimental effort it triggered produced some of the most precise tests of the equivalence principle ever performed. It pushed the limits of gravitational measurements to extraordinary sensitivity, and it established a template for how fifth force searches would be conducted in the decades that followed. You look for tiny deviations from the predictions of known forces. You test whether different materials behave differently under gravity. You search for forces that depend on composition, distance, or environment in ways that the four known forces cannot explain. And you hold every claimed detection to the highest possible standard of scrutiny. Beyond laboratory anomalies, there are cosmological puzzles so large they reshape the entire fifth force conversation. The most profound of these is dark matter. We've already touched on the basic idea that galaxies contain far more mass than we can see. But the evidence for dark matter runs deeper than that, and the failure to identify it opens a door that a fifth force could potentially walk through. The story begins in 1933, when Swiss astronomer Fritz Zwicky studied the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity. Zwicky measured how fast the galaxies in the cluster were moving and calculated how much mass would be needed to hold the cluster together. The answer was shocking. The galaxies were moving so fast that the visible matter in the cluster couldn't generate enough gravitational pull to keep them bound. There had to be far more mass than what was visible. Zwicky called it missing mass. His result was largely ignored for decades. Then, in the 1970s, astronomer Vera Rubin and her colleague Kent Ford studied the rotation curves of individual galaxies. They measured how fast stars orbit the centers of spiral galaxies at different distances. According to Newton's laws and the visible distribution of matter, stars far from the galactic center should orbit more slowly, just as outer planets in our solar system orbit the Sun more slowly than inner planets. But Rubin and Ford found that the rotation curves were flat. Stars at the edges of galaxies were orbiting just as fast as stars much closer to the center. The only explanation, within conventional gravitational physics, was that each galaxy was embedded in a massive halo of invisible matter, extending far beyond the visible disk. This was dark matter. Since then, the evidence has become overwhelming. Gravitational lensing shows that galaxy clusters bend light far more than their visible matter can account for. The cosmic microwave background, the radiation left over from the early universe, has a pattern of hot and cold spots that can only be explained if the universe contains large amounts of non-luminous matter. The Bullet Cluster, a pair of colliding galaxy clusters, shows a separation between where the visible matter is and where the gravity is, direct visual evidence that most of the mass is invisible. Dark matter is not controversial. Its gravitational effects are measured and confirmed. What's controversial is what it is. For decades, the leading hypothesis has been that dark matter consists of a new type of particle, one that interacts through gravity and possibly through the weak force, but not through electromagnetism. Physicists have built enormous underground detectors filled with liquid xenon or germanium crystals, waiting for a dark matter particle to collide with an atom and produce a detectable signal. They've searched for dark matter production at the Large Hadron Collider. They've looked for dark matter annihilation signals in gamma rays from the galactic center. Nothing. Decades of searching, hundreds of millions of dollars in experiments, and no confirmed direct detection. This persistent non-detection has pushed some physicists to consider more radical possibilities. What if dark matter doesn't interact through the weak force at all? What if it interacts through a completely new force, a dark force, mediated by a dark photon or some other hidden boson? In these models, dark matter particles interact with each other through a fifth force that has no direct effect on ordinary matter, or only an extremely faint one. This dark sector would be an entire hidden layer of physics, complete with its own particles, its own force carriers, and its own interaction rules, running parallel to the physics we see, but barely touching it. The only bridge between our world and the dark sector would be gravity, and possibly tiny, almost imperceptible couplings between dark photons and regular photons. This is not wild speculation. These are models published in serious journals by respected theorists. They're motivated by the failure of conventional dark matter searches and by the mathematical consistency of the frameworks. A dark force could explain not only what dark matter is, but also certain puzzles in the distribution of dark matter within galaxies that gravity alone struggles to account for. Some simulations of galaxy formation predict that dark matter should clump more tightly at the centers of galaxies than observations show. A self-interaction among dark matter particles, mediated by a dark force, could smooth out those central clumps and bring simulations into agreement with reality. It's worth pausing here to understand just how hard physicists have looked for dark matter particles directly, because the scale of the effort matters for the fifth force question. If dark matter were a conventional particle that interacts through the weak force, we should have found it by now. The fact that we haven't is one of the strongest reasons some physicists are looking beyond the four known forces for an explanation. The most sensitive dark matter detectors in the world sit deep underground, shielded beneath hundreds or thousands of meters of rock to block cosmic rays and other background radiation that would overwhelm the signal. The principle behind these experiments is straightforward. You fill a large tank with an ultra-pure target material, usually liquid xenon, and you wait. If a dark matter particle drifts through the detector and collides with a xenon nucleus, the collision produces a tiny flash of light and a small burst of electric charge. Sensitive photodetectors lining the walls of the tank can pick up both signals, and by analysing their timing and intensity, physicists can determine whether the collision was caused by a dark matter particle or by something mundane, a stray neutron, a radioactive decay inside the detector materials, or some other known background. The Lux Zeppelin experiment, known as LZ, operates nearly a mile underground in a former gold mine in South Dakota. It contains about 10 metric tons of liquid xenon, making it one of the largest and most sensitive dark matter detectors ever built. The Xenon NT experiment, located beneath a mountain in central Italy at the Gran Sasso National Laboratory, is a comparable instrument using roughly 6 metric tons of xenon. Both experiments have been collecting data with extraordinary sensitivity. They can detect individual photons of light and individual electrons of charge. They can distinguish a genuine nuclear collision from a background event with remarkable reliability. And both have reported results that tell the same story. No dark matter particles detected. The sensitivity of these instruments is staggering. They can rule out dark matter particles with interaction strengths down to levels that would have seemed impossibly faint a decade ago. If dark matter interacts with ordinary matter through the weak force at the strengths most models predicted, these experiments should have seen dozens or hundreds of collisions by now. They've seen none. 0 confirmed dark matter events above background. This is not a failure of the experiments. The instruments are working exactly as designed. It's a failure of the hypothesis, or at least a serious challenge to it. The simplest models of dark matter, the ones where dark matter particles interact through the weak force with strengths comparable to neutrinos, are being systematically excluded. The parameter space is shrinking. Each year of data pushes the limits further, and this is precisely why those dark sector models we discussed are gaining traction. The idea of a hidden force mediating interactions among dark matter particles was once a fringe theoretical curiosity. Now, with conventional detection methods hitting wall after wall, it's becoming one of the more natural explanations still standing. The dark matter might be perfectly interactive. It might have rich and complex physics of its own. But all of that interaction would flow through a channel we haven't built instruments to detect. The particles would be invisible to our xenon tanks and germanium crystals, not because they barely interact with anything, but because they interact with each other through a force that doesn't touch our atoms. Our detectors are listening on the wrong frequency. There's another approach to the dark matter puzzle that takes an even more radical step. Instead of proposing new particles or new forces to explain the missing mass, some physicists have asked whether the problem lies not with the matter, but with gravity itself. What if gravity doesn't behave the way we think it does at very low accelerations? This idea was proposed in 1983 by Israeli physicist Mordechai Milgrom and is called Modified Newtonian Dynamics, or MOND. The core idea is simple but provocative. Newton's law of gravity works brilliantly in the solar system, where gravitational accelerations are relatively large. But in the outer regions of galaxies, where stars orbit very slowly and the gravitational pull from visible matter is incredibly weak, the accelerations are tiny, far smaller than anything we experience on Earth or even in the solar system. Milgrom proposed that below a certain critical acceleration, roughly 10 to the minus 10 meters per second squared, a value he called A0, gravity behaves differently. It doesn't weaken as quickly with distance as Newton's law predicts. Instead, it falls off more slowly, producing a stronger pull at large distances than you'd expect. This single modification, with just one new parameter, reproduces the flat rotation curves of galaxies with remarkable accuracy. Without invoking any dark matter at all, MOND explains why stars at the edges of galaxies orbit as fast as they do. It predicts the relationship between a galaxy's visible mass and its rotation speed, a relationship called the baryonic Tully-Fisher relation, with a precision that dark matter models struggle to match without fine-tuning. For individual galaxies, MOND works disturbingly well. but MOND has serious problems at larger scales. It cannot explain the bullet cluster, where gravitational lensing clearly shows mass separated from visible matter, something that's natural if dark matter exists as actual particles, but very hard to explain if you're just modifying gravity. MOND also struggles with the cosmic microwave background. The detailed pattern of temperature fluctuations in that ancient radiation is beautifully explained by standard cosmology with dark matter. MOND, in its original form, doesn't reproduce that pattern. Relativistic extensions of MOND exist, but they're complicated and less elegant than the original idea. They often require additional fields that begin to look suspiciously like the dark matter or fifth force mediators they were trying to avoid. So MOND occupies a strange place in the fifth force conversation. It's not a fifth force in the strict sense, because it modifies an existing force rather than adding a new one. But the modification itself implies new physics. If gravity genuinely changes character at low accelerations, there must be a reason. There must be a field or a mechanism that produces this transition. And that field, whatever it is, would constitute new physics beyond the standard model and beyond general relativity. MOND might not be the right answer. Most physicists think it probably isn't. But the fact that such a simple modification works so well for galaxies is itself a clue. It's an anomaly of a different kind, not a discrepancy in a single experiment, but a suspicious pattern across thousands of galaxies that seems to be pointing towards something the standard framework doesn't capture. Then there is the puzzle of the accelerating universe. In 1998, two teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, independently discovered that the expansion of the universe is not slowing down as everyone expected. It's speeding up. Distant Type 1a supernovae, which serve as cosmic distance markers because they all explode with roughly the same intrinsic brightness, were fainter than expected. This meant they were farther away than predicted. The universe's expansion was accelerating. Something was pushing space apart. This something was named dark energy, and it accounts for roughly 68% of the total energy content of the universe. The simplest explanation is the cosmological constant, a fixed energy density of empty space itself that Einstein originally introduced into his equations and later abandoned. If the cosmological constant is the answer, dark energy is not really a force. It's just a property of the vacuum. But the cosmological constant has problems. Its predicted value from quantum field theory is absurdly larger than the observed value, off by roughly 120 orders of magnitude. This is sometimes called the worst prediction in the history of physics. Something is clearly wrong or missing in our understanding. An alternative is that dark energy is not a constant at all, but a dynamic field, a field that permeates all of space and whose energy density changes over time. This kind of field is sometimes called quintessence, and here is where the fifth force question becomes directly relevant. A dynamic field that pervades the universe and affects the expansion rate of space could also mediate a new force between particles. If matter interacts with the quintessence field, however weakly, that interaction would constitute a fifth force. It would be extraordinarily weak and extraordinarily long-ranged, but it would be real. Some models even predict that such a force would vary depending on the local environment, being screened or suppressed in regions of high density like the interior of the Earth or the solar system, and only becoming apparent in the sparse voids between galaxy clusters. This is not a coincidence or a convenient loophole. It's a natural mathematical consequence of certain field theories. Fields that couple to matter and also drive cosmic acceleration often have built-in screening mechanisms. They hide themselves precisely where we're best equipped to look for them. And the dark energy puzzle has deepened recently in a way that directly bears on the fifth force question. In 2024, the dark energy spectroscopic instrument known as DESI released its first major results. DESI is a massive survey instrument mounted on a telescope in Arizona that measures the distances and velocities of millions of galaxies and quasars. By mapping how galaxies are distributed across enormous volumes of space, DESI traces the expansion history of the universe with unprecedented detail. The expansion history matters because it tells you how dark energy has behaved over time. If dark energy is the cosmological constant, its energy density never changes. It's the same today as it was 5 billion years ago, and it will be the same 5 billion years from now. The expansion history would follow a specific, predictable curve. But DESI's early results hinted at something unexpected. The data showed subtle signs that dark energy's influence may not be constant. It may have been weaker in the past and stronger now, or it may be varying in ways that a simple cosmological constant cannot explain. The hints are preliminary. They're not at the level of statistical significance needed to claim a discovery. But they're consistent with a dynamic field, a quintessence-type field, whose energy density evolves over cosmic time. If those hints hold up as DESI collects more data over the coming years, it would be strong evidence that dark energy is not just a property of empty space, but an active field. And an active field that couples to matter, however weakly, would generate a fifth force. The DESI results are being watched very closely by physicists on both sides of the fifth force question, because they could transform the conversation from theoretical possibility to observational necessity. This is why the fifth force question is so challenging and so fascinating. The anomalies don't point to a single clear answer. The Muon G-2 anomaly hints at a new particle or interaction at the subatomic scale. The Atomkey nuclear anomaly suggests a new boson at 17 mega-electron volts, mediating a short-range force. Dark matter's invisibility opens the door to an entire hidden sector with its own forces. Dark energy's mysterious behavior could involve a field that generates the weakest imaginable long-range interaction. These are different puzzles at wildly different scales, and there's no guarantee they're connected. A fifth force, if it exists, might explain one of these puzzles and have nothing to do with the others. Or it might tie several of them together in ways we haven't yet imagined. But the most important thing to understand about all of these anomalies is what they are not. They are not discoveries. Not yet. The Muon G-2 discrepancy depends on unresolved theoretical calculations. The X-17 particle has not been independently confirmed. Fishbach's fifth force was ruled out. Dark matter and dark energy are observed phenomena, but we don't know their underlying physics. Every single one of these cracks could close. The Muon anomaly could vanish when theorists agree on the correct calculation. The X-17 could turn out to be a systematic error in the Atomkey detector. Dark matter could be a conventional particle that we simply haven't found yet. Dark energy could be the cosmological constant after all, and the mismatch with quantum field theory could be resolved by some insight we haven't had yet. Or the cracks could widen. The Muon anomaly could be confirmed as a genuine failure of the standard model, pointing to a new interaction. The X-17 could be replicated at an independent laboratory and recognized as the first direct evidence for a fifth force mediator. Dark matter searches could reveal that the dark sector contains its own forces and particles. Dark energy observations could show that the expansion rate varies in ways that only a dynamic field can explain. This is the state of play. The cracks are real, the anomalies are measured, the puzzles are documented. But none of them, on their own or together, constitute proof of a fifth force. What they constitute is something equally important: motivation, justification, reason to keep looking. In science, you don't search for something unless you have reason to believe it might be there. And right now, the reasons are accumulating. not as certainties, but as possibilities. Not as answers, but as questions that refuse to go away. The history of physics tells us that when anomalies persist across different experiments, different scales, and different methods, they often point to something real. The anomalies in the orbit of Mercury persisted for decades before Einstein's general relativity explained them. The anomalies in black body radiation persisted until Max Planck introduced quantum theory. The anomalies in beta decay energy spectra persisted until Wolfgang Pauli proposed the neutrino, a particle so elusive it wasn't directly detected for another 26 years after he predicted it. Anomalies are not noise. They're signals, faint, ambiguous, easily misread, but signals. And the anomalies we see today, in muon experiments, in nuclear decays, in the behavior of galaxies and the expansion of the cosmos, might be telling us something we're not yet ready to hear. That the universe operates on more than 4 forces, that there is an interaction hiding in the gaps, too weak or too short-ranged or too cleverly screened to have been caught by the experiments we've run so far. That the architecture of reality has a room we haven't found yet, and the only way to know for sure is to keep pushing, keep measuring, keep testing. Because the universe doesn't reveal its secrets easily. It makes you earn them, one stubborn anomaly at a time. Up to this point, we've looked at the cracks, the anomalies, the discrepancies, the puzzles that sit just outside what the 4 known forces can explain. But anomalies alone don't give you a 5th force. An anomaly tells you something might be missing. It doesn't tell you what that something is. To go further, you have to ask a much harder question. What would a 5th force actually need to look like? Not as a vague concept, not as a science fiction device, but as a real physical interaction that fits into the mathematical framework we use to describe the universe. Because in physics, a force isn't just a name you give to something unexplained. It has specific, non-negotiable requirements. It has to work in a very particular way. And understanding those requirements is essential if you want to separate genuine possibilities from wishful thinking. So let's start at the foundation. What does it take for something to qualify as a fundamental force in modern physics? The answer comes from quantum field theory, the mathematical framework that underpins the Standard Model and describes how particles and forces work at the deepest level we currently understand. In quantum field theory, every fundamental force has 3 essential ingredients. First, there must be a field. A field in physics is something that exists everywhere in space and has a value at every point. You're already familiar with fields even if you don't realize it. Temperature is a field. At every point in a room, the air has a temperature. That temperature varies from place to place, but there's a value everywhere. A gravitational field fills all of space. At every point near the Earth, the field has a strength and a direction pointing toward the center of the planet. Electromagnetic fields permeate the universe. At every point, there's an electric field value and a magnetic field value, even if both happen to be 0 in empty space far from any charge. The fields that give rise to fundamental forces are quantum fields. They obey the rules of quantum mechanics, which means they can fluctuate, they have uncertainty, and their excitations come in discrete lumps that we observe as particles. The electromagnetic field, when excited, produces photons. The fields associated with the strong force produce gluons. The weak force fields produce W and Z bosons. Each force has its own underlying quantum field. Second, there must be a mediator particle. This is the boson that carries the interaction. When 2 particles interact through a force, what's really happening is that they're exchanging these mediator bosons. The photon mediates electromagnetism, gluons mediate the strong force. The W and Z bosons mediate the weak force. The hypothetical graviton would mediate gravity, though we haven't detected gravitons yet. The properties of the mediator particle determine the properties of the force. If the mediator is massless, like the photon, the force has infinite range. Electromagnetism and gravity both reach across the entire observable universe because their mediators have zero mass. If the mediator is massive, like the W and Z bosons, the force has a limited range. The heavier the mediator, the shorter the range. The W boson's mass gives the weak force a range of less than 1% of a proton's diameter. This relationship between mediator mass and force range comes from the Heisenberg uncertainty principle. A massive mediator can only exist briefly before it must be reabsorbed or decay. The heavier it is, the less time it can exist, and the shorter the distance it can travel. This constrains the range of the interaction to a tiny region around the source particle. Third, there must be a coupling. The force must actually interact with matter. The field and its mediator particle must connect to the particles we observe, the quarks, leptons, and other constituents of the universe. This coupling determines how strongly the force acts. Electromagnetism couples to electric charge. Anything that carries charge feels the electromagnetic force. The strong force couples to color charge, a property carried only by quarks and gluons. The weak force couples to weak isospin, a quantum number carried by all quarks and leptons. A fifth force would need to couple to some property of matter. It might couple to baryon number, the total count of protons and neutrons. It might couple to lepton number. It might couple to mass itself, or to some entirely new quantum number we haven't identified yet. The nature of the coupling determines which particles feel the force and which don't. It determines the signatures the force would leave in experiments. And it's one of the main tools physicists use to search for or constrain a fifth force. These three ingredients, field, mediator, and coupling, are not optional. They're what define a fundamental interaction in the modern framework. Without a field, there's no mechanism for the force to propagate through space. Without a mediator, there's no quantum description of how the interaction works. Without a coupling to matter, the force might exist mathematically, but would be physically undetectable. It would be a ghost in the equations, present in theory, but absent from reality. A genuine fifth force needs all three. And importantly, each ingredient is something that can, in principle, be measured. Now, what kinds of mediators could a fifth force have? This is where the physics gets rich and the possibilities multiply. In the standard model, force-carrying bosons come in specific types, classified by their spin. Spin is an intrinsic quantum property of particles, a kind of angular momentum that doesn't come from physical rotation. It's built into the particle's identity. The mediators of the known forces are all spin-1 particles, also called vector bosons. Photons, gluons, W bosons, and Z bosons are all spin-1. The graviton, if it exists, would be spin-2, which reflects the unique geometric nature of gravity. But a fifth force mediator doesn't have to follow these patterns. It could be a spin-1 vector boson, similar to the photon, but associated with a new type of charge. It could be a spin-0 scalar boson, a particle with no spin at all, similar in some ways to the Higgs boson. The type of mediator changes everything about how the force behaves. A new vector boson would generate a force that closely resembles electromagnetism in structure. It would produce interactions between particles that carry whatever new charge the boson couples to. The force could be attractive or repulsive, depending on the charges involved. Its range would depend on the boson's mass. A massless vector boson would produce an infinite range force. A massive one would produce a short-range force. The X17 particle proposed to explain the Atomkey anomaly would be precisely this kind of particle, a new vector boson with a mass of about 17 mega-electron volts, mediating a very short-range interaction between nucleons. Some theoretical models propose that such a boson could arise from a hidden gauge symmetry, a symmetry of nature that operates in a sector of physics we haven't yet accessed experimentally. In the standard model, Each force is associated with a mathematical symmetry group. Electromagnetism corresponds to a symmetry called U1. The weak force and electromagnetism together correspond to a larger symmetry. The strong force has its own symmetry group. A fifth force could correspond to an additional symmetry, a hidden U1, for instance, that generates its own vector boson. This hidden boson might interact with ordinary matter only very weakly, through tiny couplings that make it almost invisible in current experiments. A scalar boson mediator would produce a different kind of force. Scalar fields are simpler in structure than vector fields. They have a value at every point in space, but no direction, like temperature. The Higgs field is a scalar field, and the Higgs boson is its excitation. A new scalar field pervading the universe could generate an attractive force between all particles that couple to it. This force would always be attractive, never repulsive. It would look somewhat like an additional gravitational pull, but with different properties, possibly different range, different strength, different coupling to different types of matter. In fact, scalar fields are one of the most natural candidates for a fifth force, precisely because they arise so readily in extensions of current physics. Many theories that attempt to go beyond the standard model, including string theory and various grand unified theories, predict the existence of light scalar fields. These fields would be present everywhere in the universe, and their interactions with matter would constitute a fifth force. One of the most important tools for understanding how a fifth force would behave is something called the Yukawa interaction. In 1935, Japanese physicist Hideki Yukawa proposed a mathematical framework to describe a force with finite range. His original work was aimed at the strong nuclear force, which acts only over nuclear distances. Yukawa showed that if the force is mediated by a massive particle, the strength of the interaction falls off exponentially with distance, much faster than the gradual weakening of gravity or electromagnetism. The result is a force that's strong at short range but effectively vanishes beyond a certain distance, determined by the mediator's mass. The heavier the mediator, the faster the fall-off and the shorter the range. This Yukawa framework has become the standard template for modelling a fifth force. You specify 3 parameters: the strength of the coupling, the mass of the mediator, and what the force couples to. From those 3 numbers, you can calculate how strong the force would be at any given distance, what its effects would be on laboratory experiments, and where in the range versus strength landscape it might be hiding. And this brings us to a crucial point. A fifth force doesn't have to be strong. In fact, the whole reason it could have escaped detection is that it might be extraordinarily weak. Consider how weak gravity is at the particle level. The gravitational attraction between 2 protons is roughly 10 to the 36 times weaker than the electromagnetic force between them. Gravity is laughably feeble at small scales. We only notice it because it's always attractive and it adds up over enormous amounts of matter. A fifth force could be even weaker than gravity, or it could be stronger than gravity but shorter ranged, confined to distances so small that no experiment has probed them carefully enough. Or it could operate at cosmological distances but with a strength so faint that its effects are swamped by ordinary gravity in any local measurement. The search for a fifth force is essentially a search through a vast 2-dimensional landscape. One axis is strength, the other is range. And different experiments probe different regions of that landscape. Torsion balance experiments are exquisitely sensitive at ranges from a fraction of a millimeter to several meters. Lunar laser ranging, which bounces laser beams off reflectors left on the Moon by Apollo astronauts, tests gravity at Earth-to-Moon distances with extraordinary precision. Satellite experiments test the equivalence principle in the near-Earth environment. Observations of binary pulsars test gravity at stellar system scales. Cosmological measurements probe interactions at the scale of galaxy clusters and beyond. Each experiment rules out a certain patch of the landscape. If a fifth force existed with strength X and range Y, a particular experiment would have seen it. Since it didn't, that combination is excluded. Over decades, these exclusions have mapped out a detailed picture of where a fifth force cannot be. But the landscape is enormous, and there are vast regions that remain unexplored. This is where some of the most creative theoretical work comes in, because it turns out that certain types of fifth force fields have a built-in ability to hide. They don't just happen to be hard to detect, they're constructed by the mathematics of the field theory itself to suppress their effects precisely where we're most likely to look. These are called screening mechanisms, and they represent some of the most ingenious ideas in modern theoretical physics. The most famous screening mechanism is the chameleon mechanism. A chameleon field is a scalar field that changes its effective mass depending on the local density of matter. In regions of high density, like inside the Earth, inside a laboratory, or even inside the atmosphere, the field becomes very heavy. And as we discussed, a heavy mediator produces a short-range force. So in a high-density environment, the chameleon force is effectively suppressed. Its range shrinks to microscopic distances, and its effects become undetectable. But in regions of low density, like the vast empty spaces between galaxies, the field becomes very light. Its range extends to cosmological distances. In these sparse environments, the chameleon force could be significant, potentially contributing to cosmic acceleration or modifying the behavior of gravity at the largest scales. This means a chameleon field could be driving the expansion of the universe while remaining completely hidden from every laboratory experiment on Earth. The field literally changes its character depending on where it is, like a chameleon changing color to match its surroundings. This is not a contrived trick. The mathematics is natural and follows straightforwardly from certain types of scalar field theories. The chameleon mechanism arises from the interplay between the field's self-interaction and its coupling to matter density. It's an elegant consequence of the equations. Another screening mechanism is the symmetron mechanism. A symmetron field has a symmetry that is restored in high-density environments. When the field is in a symmetric state, it doesn't couple to matter and produces no fifth force. But when the density drops below a threshold, the symmetry breaks spontaneously and the field develops a coupling to matter. The force turns on. In dense environments like our solar system, the symmetron is in its symmetric phase and effectively invisible. In the cosmic voids between galaxy clusters, the symmetry is broken and the force becomes active. This is a fundamentally different hiding strategy from the chameleon, but the end result is similar. The force conceals itself where we're best equipped to detect it. A third mechanism is the Weinstein mechanism, named after physicist Arkady Weinstein. This mechanism suppresses the force near massive objects through the nonlinear dynamics of the field. Close to a large mass like the Earth or the Sun, the field's behavior becomes highly nonlinear, and these nonlinear effects effectively screen the fifth force. Far from massive objects, the field behaves linearly, and the force operates at its full strength. The Weinstein mechanism was originally discovered in the context of massive gravity theories, where physicists explored whether the graviton itself could have a small mass. Giving the graviton mass changes the behavior of gravity at large distances and introduces additional degrees of freedom that could act as a fifth force. The Weinstein mechanism ensures these extra effects are suppressed near massive bodies, preserving the success of general relativity in the solar system while allowing modifications at cosmological scales. Each of these screening mechanisms has a common theme. The fifth force isn't uniformly hidden, it's selectively hidden. It suppresses itself in the environments where our instruments operate and reveals itself in environments we can barely access. This makes the search incredibly challenging, but it also makes it scientifically precise, because each mechanism makes specific, testable predictions about exactly where the force transitions from screened to unscreened. If you can probe the right environment, the right density, the right distance scale, you can catch the force in the act of emerging from its hiding place. This brings us to an important distinction that's easy to blur. Not every mysterious cosmic phenomenon is a fifth force. Dark energy, for example, is often discussed alongside the fifth force question. And there's good reason for that. If dark energy is caused by a dynamic scalar field like quintessence, and if that field couples to ordinary matter, then yes, quintessence would generate a fifth force. The field would mediate an interaction between particles carried by the scalar boson excitations of the field, with the strength and range determined by the field's properties. In this scenario, the thing driving the expansion of the universe and the thing creating a new force would be the same entity, the same field, doing both jobs simultaneously. But dark energy doesn't have to be a fifth force. If dark energy is simply the cosmological constant, a fixed energy density of the vacuum with no dynamics and no coupling to matter, then it doesn't mediate any interaction. It affects the expansion of space through general relativity, but it doesn't create a force between particles. There's no mediator boson, there's no coupling. It's a property of empty space, not an interaction between objects. The distinction matters because it determines what you look for experimentally. If dark energy is a cosmological constant, you study the expansion history of the universe and the geometry of spacetime. If dark energy is a dynamic field with a coupling to matter, you also look for fifth force effects, tiny deviations in how matter behaves, violations of the equivalence principle, anomalous accelerations at specific distance scales. The two scenarios lead to different experimental programs. The same caution applies to dark matter. Dark matter's existence is inferred entirely from its gravitational effects. If dark matter consists of particles that interact only through gravity and through no other force, then it doesn't point to a fifth force at all. It's just a new type of matter, interacting through a known force. But if dark matter particles interact with each other through a dark force, mediated by a dark photon or a dark scalar boson, then that dark force is a genuine fifth interaction, even if it barely touches ordinary matter. And if there's even a tiny coupling between the dark sector and the visible sector, if dark photons can occasionally convert into regular photons or interact with electrons at incredibly suppressed rates, then the dark force leaks into our world and becomes detectable, at least in principle. So when physicists talk about a fifth force, they're talking about something specific. A new quantum field that pervades space, a mediator boson associated with that field, a coupling between the field and matter that produces a measurable physical effect. The force has to obey the laws of quantum mechanics. It has to be consistent with special relativity. Its consequences have to be calculable, and those calculations have to be testable against experiment. This is what separates the scientific search for a fifth force from vague speculation. It's grounded in a precise mathematical framework. You can write down the equations, you can compute the predictions, you can design experiments to look for the effects, and you can definitively confirm or rule out specific models. The landscape of fifth force models is vast. Hidden vector bosons coupling to baryon number, ultralight scalar fields coupling to mass, chameleon fields that screen in dense environments, symmetron fields that restore their symmetry near matter, dark photons coupling to a hidden sector, Yukawa interactions with ranges from subatomic to cosmological. Each model occupies a specific region of the strength versus range landscape. Each makes specific predictions about where its effects would show up, and each can be targeted by specific experiments designed to probe exactly that region. What unifies all these models is the recognition that the four known forces, as successful as they are, might not be the whole story. The mathematical frameworks we use to describe the universe are flexible enough to accommodate additional interactions. There is no theorem in physics that says 4 forces is the maximum. There's no principle that prohibits a fifth field from existing. The equations allow it. The question is whether nature actually makes use of that possibility, and the answer has to come from experiment, not from theoretical elegance, not from mathematical beauty, not from philosophical preference. From measurement, from data, from the stubborn, patient work of building instruments sensitive enough to detect an interaction that the universe may have hidden extraordinarily well. A fifth force, if it exists, isn't going to announce itself. It isn't going to show up as a dramatic departure from known physics in a standard experiment. It's going to appear as a whisper, a tiny deviation in a measurement that should have been zero, a faint signal riding beneath the noise, a subtle pattern in data that only becomes visible when you know exactly where and how to look. Finding it, or definitively ruling it out, requires understanding precisely what it would need to be. That's what the theoretical framework provides. Not certainty about what exists, but clarity about what to look for. And right now, physicists know what to look for with remarkable specificity. They know the shapes of the possible forces. They know the masses of the possible mediators. They know the strengths of the possible couplings. They know which experiments could catch which candidates. The net is being tightened, experiment by experiment, measurement by measurement, exclusion by exclusion. And somewhere in the remaining open territory, in the patches of the landscape that haven't been checked yet, a fifth force might be waiting. Or it might not. But either way, finding the answer will teach us something profound about the universe we live in. Because ruling out a possibility with precision is just as valuable as confirming one. Every region of the landscape that's searched and found empty tells us something real about what nature allows and what it doesn't. The absence of a fifth force in a given regime is not a failure, it's information. And information, accumulated carefully over decades, is how physics advances. So if the anomalies are real, if the theoretical frameworks allow it, if there's room in the equations for a fifth force to exist, why haven't we found one? This is the question that separates speculation from science, because the absence of evidence is not nothing. In physics, null results are data. Experiments that look for something and don't find it are telling you something precise and valuable. They're drawing boundaries. They're closing doors. They're mapping the territory where a fifth force cannot be, and, in doing so, narrowing down the territory where it still could be. Over the last 40 years, some of the most sensitive instruments ever built by human beings have been aimed directly at the fifth force question. And every single one of them has come back with the same answer: no confirmed detection. That track record deserves serious attention, because it's not a track record of failure, it's a track record of extraordinary measurement, and it tells us something important about the universe. Let's start with the experiments that test the equivalence principle, the idea that all objects fall at the same rate regardless of their composition. This is one of the cornerstones of general relativity. If a fifth force couples to some property of matter other than mass, like baryon number or the ratio of protons to neutrons, then different materials would respond differently to that force. Objects made of different elements would fall at slightly different rates. The equivalence principle would be violated. Testing this is conceptually simple. You take two objects made of different materials and you measure whether they accelerate at the same rate in a gravitational field. But doing it with the precision needed to detect a fifth force is extraordinarily difficult. The most sensitive ground-based tests come from a group at the University of Washington called the EOT-WASH group, named in honor of Laurent Eötvös, whose original torsion balance experiments inspired the modern program. The EOT-WASH group has built a series of torsion balances of staggering sensitivity. These instruments consist of a thin plate or ring of carefully machined material suspended from an ultrafine fibre. The plate contains test masses of different compositions, arranged so that any composition-dependent force would create a twist in the fibre. The twist is measured using laser reflections with sensitivity better than a trillionth of a degree of rotation. These experiments have tested the equivalence principle for dozens of different material pairs, beryllium and titanium, beryllium and aluminium, different isotopes of the same element, materials chosen specifically to maximize the contrast in properties that a fifth force might couple to. And the result, every time, is null. No measurable difference in how different materials respond to gravity. The equivalence principle holds to a precision of roughly 1 part in 10 to the 13. That's 1 part in 10 trillion. If a fifth force exists at the ranges and strengths these experiments probe, it would have shown up. It didn't. So those regions of the strength versus range landscape are excluded. In space, the French microscope satellite launched in 2016 pushed equivalence principle tests even further. By placing test masses in orbit around Earth, the satellite eliminated many sources of noise that plague ground-based experiments: seismic vibrations, air currents, temperature fluctuations. In orbit, the test masses are in freefall, experiencing essentially perfect gravitational conditions. Microscope compared the acceleration of platinum and titanium test masses with a precision of roughly 1 part in 10 to the 15. That's 1,000 times more precise than the best ground-based tests at the time. The result was null. No violation of the equivalence principle. No evidence of a fifth force coupling differently to different materials at these sensitivities and at the orbital distances tested. These null results are powerful constraints. They tell us that if a fifth force exists and couples to ordinary matter, its strength relative to gravity must be extraordinarily small at the distance scales probed by these experiments. The force would have to be weaker than gravity by a factor of at least 10 to the 12 or more at ranges from centimeters to the Earth-Moon distance. This doesn't rule out a fifth force entirely, but it confines it to extreme corners of the parameter space, to regions where it's either absurdly weak or active only at distances much shorter than a centimeter, or active only at distances much longer than the Earth-Moon separation, or screened by the mechanisms we discussed earlier. Short-range tests have their own experimental tradition. At distances below a millimeter, gravity itself becomes extremely difficult to measure because the electromagnetic interactions between nearby surfaces begin to dominate. Casimir forces, van der Waals forces, and electrostatic patches on metal surfaces all create backgrounds that can mimic or mask a gravitational signal. Despite these challenges, experimentalists have measured gravity down to distances of roughly 50 micrometers using micro-cantilever devices and torsion pendulums operating in carefully shielded environments. At these scales, some theories predict deviations from Newtonian gravity, particularly models with extraspatial dimensions proposed by physicists like Nima Arkani-Hamed, Savas Dimopoulos, and Gia Diwali. In these models, gravity would become stronger than expected at short distances because gravitons could propagate through the extra dimensions. The strengthening of gravity at short range would look exactly like a new force, an additional attraction beyond what Newton's law predicts. Experiments have searched carefully for this effect. They found nothing. Gravity behaves exactly as Newton described, down to the smallest distances tested. This constrains the size of any extra dimensions to be smaller than roughly 50 micrometers. If extra dimensions exist, they're extremely small, too small for current experiments to resolve. Collider experiments provide a completely different kind of constraint. At the Large Hadron Collider and other particle accelerators, physicists smash particles together at enormous energies and study what comes out. If a fifth force mediator exists, it could be produced in these collisions, either directly or through its effects on known processes. The X-17 particle proposed to explain the atom-key anomaly would have a mass of about 17 mega-electron volts. That's well within the energy range of existing accelerators. If such a particle exists and couples to quarks or electrons, it should show up in precision measurements of particle decays and scattering processes. Several experiments at CERN, at Jefferson Lab in Virginia, and at other facilities around the world have searched specifically for a new boson in the mass range around 17 mega-electron volts. The searches look for narrow resonances, sharp peaks in data that would indicate a new particle being produced and immediately decaying. So far, no independent experiment has confirmed the X17. Some searches have seen no signal at all in the relevant mass range. Others have set upper limits on how strongly such a particle could couple to ordinary matter. These limits are beginning to squeeze the parameter space of the models that explain the atom key anomaly. If the X17 exists, its coupling to electrons and quarks must be extremely small, small enough to have escaped detection in all these independent searches. That's not impossible, but it's becoming increasingly constrained. At higher masses, the Large Hadron Collider has searched for new force-carrying particles across a vast range. Heavy vector bosons, called Z-prime particles in theoretical models, have been looked for in the data from proton-proton collisions at energies up to 13,600 giga-electron volts. No Z-prime has been found. The absence of a signal sets lower limits on the mass of any such particle, typically pushing it above several thousand giga-electron volts, depending on its coupling strength. For lighter mediators, precision measurements of known particle properties serve as indirect probes. The Muon G-2 measurement is a perfect example. If a new light boson couples to muons, it would shift the muon's anomalous magnetic moment by a calculable amount. The persistent discrepancy in G-2 could be explained by such a particle, but the particle must simultaneously avoid detection in all other experiments that would be sensitive to it. This is a tight needle to thread. Models that explain G-2 while evading all other constraints exist, but they require very specific properties, particular mass ranges, particular coupling patterns, particular decay channels. Each new null result from another experiment makes the needle narrower. Astrophysical observations add another layer of constraint. Stars, for instance, are extraordinarily sensitive probes of new light particles. If a fifth force mediator is light enough, it can be produced inside the hot, dense cores of stars. Once produced, it can escape the star, carrying away energy. This additional energy loss would change how stars evolve, how long they burn, how quickly they cool when they die. Observations of stellar evolution, particularly the cooling rates of white dwarfs and neutron stars, and the duration of neutrino signals from supernovae, set tight limits on the properties of any new light particle. The supernova that occurred in the Large Magellanic Cloud in 1987, observed as SN 1987A, produced a burst of neutrinos detected on Earth. The number and timing of those neutrinos matched predictions from standard stellar physics. If a new light boson had been draining energy from the collapsing core, the neutrino signal would have been shorter or weaker. It wasn't. This constrains the coupling of any new light boson to nuclear matter. Cosmological observations provide constraints at the largest scales. The cosmic microwave background, the afterglow of the Big Bang, encodes information about the forces and particles that existed in the early universe. If a fifth force was active in the first few 100,000 years after the Big Bang, it would have affected how matter clumped together, how sound waves propagated through the primordial plasma, and how the pattern of hot and cold spots in the microwave background formed. The observed pattern matches the predictions of standard cosmology, with the four known forces to remarkable precision. There is very little room for an additional interaction at the strengths and ranges that would leave an imprint on these observations. So the picture that emerges from decades of searching is this. No fifth force has been confirmed. Every experiment designed to detect one has returned a null result. The equivalence principle holds to 1 part in 10 to the 15. Gravity follows Newton's law down to 50 micrometers. No new force-carrying particles have been produced at colliders. Stellar evolution matches standard physics. The cosmic microwave background fits standard cosmology. The landscape of excluded parameter space is enormous and growing, and yet the search continues. Why? because the null results, as impressive as they are, don't cover everything. They rule out large swathes of the landscape, but they leave others untouched. A fifth force that is screened by a chameleon or symmetron mechanism would evade equivalence principle tests conducted in the high-density environment of Earth's surface. A force mediated by an ultralight boson with a mass of 10 to the minus 22 electron volts or less would have a range comparable to the size of galaxies, well beyond what laboratory experiments can probe. A force that couples exclusively to dark matter and has negligible interaction with ordinary matter would be invisible to every experiment using ordinary matter as a detector. A force that operates only at distances below 50 micrometers could be hiding just beyond the reach of current short-range gravity tests. The exclusions are definitive within their domains, but the domains have boundaries, and beyond those boundaries, the question remains open. This is why the next generation of experiments matters so much. Physicists are not blindly repeating old searches. They are designing instruments specifically to probe the unexplored regions, the corners of parameter space where a fifth force could still be hiding. And several of these experiments represent genuine leaps in sensitivity. Atom interferometry is one of the most promising new approaches, and it deserves a closer look, because the way it works reveals just how creative physicists have become in hunting for interactions that might be unimaginably faint. The basic principle exploits one of quantum mechanics' strangest properties. At the quantum level, atoms don't just travel along a single path. They can exist in a superposition of traveling along multiple paths simultaneously. An atom interferometer takes advantage of this by splitting a cloud of ultra-cold atoms into two groups, using a precisely timed laser pulse. One group follows one path through space. The other follows a slightly different path. After a set time, another laser pulse recombines them. When the two groups reunite, they interfere with each other, just like overlapping ripples in a pond. If both groups experienced exactly the same forces during their separate journeys, they recombine perfectly. The interference pattern is clean and predictable. But if one group experienced even the tiniest additional force, a force that the other group didn't feel or felt differently, the interference pattern shifts. That shift can be measured with extraordinary precision. The beauty of this approach is its sensitivity. Because the atoms are in quantum superposition, the interferometer is sensitive to forces at a level that would be completely invisible to a classical instrument. A torsion balance measures the twist on a macroscopic object. An atom interferometer measures the quantum phase shift of individual atoms. These are fundamentally different kinds of measurements, and they're sensitive to different kinds of forces. In particular, atom interferometers are extraordinarily sensitive to forces produced by ultralight mediators, bosons so light that their corresponding force has a range of meters, kilometers, or even larger. These are precisely the mediators predicted by certain dark matter models and by some quintessence theories. The MAGIS 100 experiment takes this concept to an extreme scale. Instead of a tabletop apparatus a few meters tall, MAGIS 100 uses a vertical shaft 100 meters deep at Fermilab. Clouds of strontium atoms are dropped from the top of the shaft, falling freely for several seconds through a vacuum. During the fall, laser pulses split, redirect, and recombine the atom clouds at precisely timed intervals. The 100-meter baseline gives the atoms a long time in freefall, which amplifies any force acting on them. The longer the atoms fall, the more time a fifth force has to nudge them, and the larger the resulting phase shift. MAGIS 100 is designed to detect accelerations as small as 10 to the minus 15 meters per second squared. That's 1 million times more sensitive than the best current atom interferometers. At that level of sensitivity, the experiment could detect forces far weaker than gravity, precisely the regime where screened scalar fields and ultralight dark matter mediators are predicted to operate. The European AION project follows the same philosophy, but with a staged approach, starting with a 10-meter prototype and eventually scaling to a multi-hundred-meter instrument, possibly located in a mine shaft or a dedicated vertical facility. Together, MAGIS 100 and Aeon will probe a region of the fifth force landscape that has never been accessible before. They represent a genuinely new capability, not just an incremental improvement on existing experiments, but a fundamentally different way of searching for new forces. Precision isotope-shift spectroscopy is another frontier. By comparing the energy levels of different isotopes of the same element with extreme precision, physicists can search for a new force that couples to neutrons. Different isotopes have different numbers of neutrons, so a force that depends on neutron number would shift their energy levels by slightly different amounts. Recent experiments using calcium ions, barium ions, and ytterbium atoms have already achieved sensitivities that constrain new forces in mass ranges that colliders cannot easily access. As laser technology and atomic clock precision continue to improve, these measurements will push into previously unexplored territory. Gravitational wave detectors, both current and planned, offer another window. The LISA space mission, expected to launch in the mid-2030s, will detect gravitational waves at frequencies far lower than what ground-based detectors like LIGO can see. LISA will observe mergers of supermassive black holes and could detect subtle deviations in gravitational wave propagation that would signal a modification of gravity or the presence of a new long-range force. If gravitational waves travel at a speed even slightly different from the speed of light, or if they exhibit dispersion where different frequencies travel at different speeds, it could indicate a massive mediator modifying gravity at large scales. The single observation of gravitational waves from a neutron-star merger in 2017, detected simultaneously in gravitational waves and light, already constrained the difference between the speed of gravity and the speed of light to less than 1 part in 10 to the 15. Future observations with LISA and next-generation ground detectors will tighten these constraints by orders of magnitude. The future circular collider proposed at CERN would be a 100-kilometer ring capable of colliding particles at energies roughly 7 times higher than the Large Hadron Collider. At these energies, physicists could produce and study particles far heavier than anything accessible today. If a fifth force mediator has a mass in the range of tens of thousands of giga-electron volts, only a machine like the future circular collider could produce it directly. Even if the mediator is too heavy to produce, its virtual effects could shift the properties of known particles in ways detectable through precision measurements. The future circular collider's precision program, colliding electrons and positrons at lower energies to make extraordinarily clean measurements, could detect these virtual effects with sensitivity surpassing anything currently possible. Independent replication of the atom key result remains a critical near-term goal. Experiments at institutions in Canada, Vietnam, Italy, and the United States are specifically designed to test whether the anomalous signal in beryllium-8 and helium-4 nuclear transitions is real. These experiments use different detector geometries, different target preparation methods, and different analysis techniques to minimize the chance that any systematic error in the original experiment could be accidentally reproduced. If even one independent group sees the same anomaly at the same angle and the same energy, the case for the X-17 particle strengthens dramatically. If none of them see it, the anomaly fades. Each of these experimental programs targets a specific region of the landscape. Atom interferometers probe ultralight mediators. Isotope-shift spectroscopy probes mediators in the electron-volt to mega-electron-volt range. Colliders probe heavy mediators. Gravitational wave observations probe modifications at cosmological scales. Equivalence principle tests in space probe composition-dependent forces at planetary distances. Together, they form a coordinated assault on the fifth force question, covering the landscape from the smallest distances to the largest, from the lightest mediators to the heaviest. And this is why the question of a fifth force is not merely academic. It's not a curiosity at the margins of physics, it sits at the intersection of nearly every major unsolved problem in fundamental science. The nature of dark matter, the origin of dark energy, the unification of gravity with quantum mechanics, the completeness of the Standard Model, the structure of space-time at the smallest scales. A confirmed fifth force would bear on all of these problems simultaneously, because it would mean the fundamental inventory of nature is different from what we thought. Think about what confirmation would actually require. You would need to identify a new field, a field not currently in the Standard Model, a field not predicted by general relativity, a field that has been pervading the universe since the beginning of time and yet has escaped every measurement humans have ever made. You would need to identify the mediator boson of that field, determine its mass, its spin, its coupling to matter. You would need to write new terms in the fundamental equations of physics, terms that modify how particles interact, how forces propagate, how matter behaves. The Standard Model would need to be extended. And depending on the properties of the force, general relativity might need to be modified as well. This is not a small thing. The Standard Model in its current form has 19 free parameters. Adding a fifth force could add several more. A new coupling constant, a new mediator mass, a new charge or quantum number. Each of these would need to be measured experimentally. But more than that, the existence of a fifth force would raise immediate follow-up questions that could reshape theoretical physics for decades. Why is the force so weak? Why hasn't it been seen before? Does it unify with any of the known forces at higher energies? Is it connected to the Higgs field? Does it operate in the dark sector? Does it play a role in the matter-antimatter asymmetry of the universe? Is it part of a larger structure we haven't yet glimpsed? To understand why confirmation would be so transformative, it helps to walk through a specific scenario in concrete detail. Let's take the X-17 particle. Imagine that tomorrow, an independent laboratory, say a group in Italy or Canada, announces that they've reproduced the atom key anomaly. They see the same excess of electron-positron pairs at the same separation angle, consistent with a new boson at 17 mega-electron volts. Then a second group confirms it, and a third. The statistical significance climbs past 5 sigma. The systematic errors are ruled out. The particle is real. What happens next? First, theorists would need to determine what kind of particle it is. A vector boson, a scalar boson, or something else. Its spin would be inferred from the angular distribution of its decay products. Suppose it's a vector boson, a spin 1 particle. That immediately implies a new gauge symmetry, a new U1 symmetry group generating this boson, analogous to how electromagnetism's U1 symmetry generates the photon. The Standard Model would need to be extended to include this symmetry. New terms would be added to the Lagrangian, the master equation that encodes all particle physics. The new boson's mass, coupling constants, and charge assignments would become free parameters to be measured. But it doesn't stop there. A new gauge symmetry often implies the existence of additional particles. Anomaly cancellation, a mathematical consistency requirement in quantum field theory, typically demands that new fermions exist to balance the equations. The theory might predict new particles that haven't been observed yet, particles that could be searched for at colliders or in precision experiments. If the X-17 couples to a quantity like B-L, the difference between baryon number and lepton number, the implications would reach into neutrino physics, into the matter-antimatter asymmetry of the universe, into the behavior of neutron stars. Cosmologically, a new light boson would have been present in the early universe. It would have contributed to the radiation energy density during the first few minutes after the Big Bang, affecting the formation of light elements during a process called Big Bang nucleosynthesis. The observed abundances of hydrogen, helium, and lithium constrain how many light particles existed in the early universe. A new boson would shift those predictions and physicists would need to check whether the shift is consistent with observations or whether the boson must have some mechanism to avoid being produced in the early universe. If the X17 couples to dark matter, even weakly, it could open a portal between the visible and dark sectors. Dark matter particles could annihilate into X17 bosons, which would then decay into electron-positron pairs. This would produce a characteristic signal in gamma-ray and cosmic ray observations, a signal that existing telescopes could search for immediately. The X17 could become the Rosetta Stone for the dark sector, the first particle we've identified that bridges the gap between the matter we see and the matter we can't. And the psychological impact on physics would be enormous. For decades, the Standard Model has stood unchallenged by any direct experimental result. Extensions have been proposed, supersymmetry, grand unification, extra dimensions, but none have been confirmed. A verified fifth force mediator would be the first confirmed particle beyond the Standard Model. It would break the dam. It would demonstrate that new physics is accessible at energies we can actually reach, not locked away at the Planck scale or hidden behind some unreachable energy barrier. It would reinvigorate experimental particle physics and redirect theoretical efforts. Careers would pivot, funding priorities would shift, new experiments would be proposed within months. Every previous discovery of a fundamental force reshaped physics in ways that went far beyond adding one more entry to a list. When electromagnetism was understood, it didn't just explain magnets and sparks. It revealed the nature of light, led to radio, led to the understanding of atoms, led to quantum electrodynamics, led to the entire framework of gauge theories. When the weak force was characterized, it didn't just explain radioactive decay. It led to the electroweak unification, to the prediction and discovery of the Higgs boson, to our understanding of how the early universe synthesized elements. When the strong force was understood through quantum chromodynamics, it didn't just explain nuclear binding. It revealed the existence of quarks and gluons, led to asymptotic freedom, deepened our understanding of confinement, and transformed particle physics. A fifth force would follow the same pattern. It wouldn't just be a new line on a list. It would be a new thread woven into the fabric of physical law. Pull on it, and the entire tapestry would shift. New particles would need to exist. New symmetries might be revealed. New connections between gravity and quantum mechanics might emerge. The hierarchy of forces, the structure of the vacuum, the evolution of the early universe, the fate of the cosmos, all of it could look different in the light of a fifth interaction. And perhaps the most profound consequence would be this: a confirmed fifth force would tell us, in the most concrete way possible, that the universe is richer than we knew, that nature has more tools, more mechanisms, more interactions than we had catalogued, that our inventory of reality was incomplete, not because we were careless or foolish, but because the force was hidden, tucked away behind screening mechanisms, or lurking at scales just beyond our instruments, or coupling to matter so faintly that decades of searching weren't quite enough to catch it. That's the real lesson of the fifth force search. Not whether the answer turns out to be yes or no, but what the search itself reveals about the nature of scientific knowledge. We don't know the universe by assuming we've found everything. We know it by testing, relentlessly and precisely, whether we've missed something. Every null result is a brick in the wall of established knowledge. Every anomaly is a crack worth investigating. And every new experiment that pushes into unexplored territory is an act of scientific courage, a willingness to ask the universe a question it might answer in a way we don't expect. Four forces have carried us remarkably far. They've explained the behavior of matter from the interior of protons to the large-scale structure of the cosmos. They've powered technologies that define modern civilization. They've revealed a universe of astonishing elegance and mathematical beauty. But 4 is not a sacred number. It's not written into the laws of logic or mathematics that reality must operate on exactly 4 interactions. 4 is simply what we've confirmed so far. The universe is under no obligation to stop there, and the cracks, the anomalies, the unexplained observations that have accumulated over decades suggest, quietly but persistently, that it might not have stopped there. Whether a fifth force is ultimately found or definitively excluded, the search will have been worth it, because either outcome transforms our understanding. Confirmation opens a new chapter in physics. Exclusion closes doors with precision and confidence, telling us the four forces truly are sufficient, that the Standard Model and general relativity, for all their incompleteness, capture more of reality than we dared hope. For now, the question stands open. The instruments are being built, the measurements are being planned, the calculations are being refined. Somewhere in the data, in the interference patterns of falling atoms, in the polarization of ancient light, in the oscillations of neutrinos, in the decay products of unstable nuclei, the answer may already be waiting. A whisper so faint that it takes the most sensitive instruments humanity has ever built to hear it. Or a silence so complete that it tells us with extraordinary certainty that four forces are all there are. Either way, we'll only know by listening, and physicists, to their credit, have never stopped.